Our project aimed to find potential exoplanets from the NASA Exoplanet database. We did this using light transit graphs. Light transit graphs measure the amount of light that comes from a star over a set period of time as seen on Earth. If a graph has consistent dips of similar size, we could deem it a potential planet due to the graph likely showing a planetary orbit.
We had to comb through about 340,000 graphs, which gave us a bit of a time problem. So we solved it by making a script system and an AI model to identify dips in a graph, and another AI model to give a confidence score based off of the graph itself.
The original aim of the project was to identify exoplanets. We have continued to develop the project and are now working on identifying the habitability of an exoplanet we have identified. This involved finding equations to get the habitable zone of the respective star and then locating the planet's position in it and using another method of identification called radial velocity. We use three main equations to do this. An equation to get the luminosity of the star, an equation to get the effective temperature of the star, and the equation for the habitable or Goldilocks zone.
From here we got a different type of graph called a spectroscopy graph. A spectroscopy graph separates all the different colors that were emitted from a star's light. From there, we used a method called the Doppler shift effect to confirm the existence of the planet. Similar to the light transit graphs, they both contain dips, a consistent dip meaning that there is a planet from that graph. We look for those dips to prove the existence of an exoplanet. We're currently working on streamlining our data collection to remove some inconsistencies. We also want to create a 3D simulation of a planet's surface, and we want to tidy up our data for better presentation. Thank you for watching our video.